At the smallest scales, the atoms in your body are vibrating, not because you're shaking, not because you're nervous, but because you're warm, because you carry energy. As long as temperature exists, motion exists. And as long as you're alive, nothing inside you ever truly rests. This idea can feel strange at first because from the outside your body looks still. Your hand doesn't blur. Your breath is slow. Everything seems calm. But calm does not mean motionless. It only means that the motion is too small, too balanced, or too familiar for your senses to notice. If we could slow time down and look closer, we would see a quiet kind of activity everywhere. Atoms shifting in place, molecules jostling softly, energy constantly being exchanged even when nothing appears to change. This is not a special property of living things. It is simply how matter behaves when it has energy. Warmth is not just a feeling. It is motion distributed across countless tiny particles, each moving in its own subtle way. Now let's move outward. You may feel still right now, but you are resting on a planet that is rotating. Earth turns steadily beneath you, carrying everything on its surface along for the ride. The reason you don't feel this motion is not because it is slow, but because it is smooth. The air moves with you. The ground moves with you. Even the oceans follow the same rotation. Stillness once again is only relative. Earth itself is not anchored in space. It is travelling around the sun in a wide continuous path that repeats year after year. And the sun does not sit at the centre of a quiet system. It drifts through the galaxy, pulling planets, asteroids and comets along with it as part of a much larger journey. There is something important hidden in this picture. You do not need effort to be in motion. You do not need intention. You are already moving simply by existing. In fact, motion is so deeply woven into the universe that true stillness would be the unusual case. A perfect absence of movement would require the removal of all energy, all temperature, all interaction. As far as we know, such a state does not naturally occur. So when we say that nothing in the universe ever truly stands still, we are not being poetic. We are describing the most ordinary condition of reality. Motion is not an exception. It is the background. We only notice it when something changes, when a planet shifts against the stars, when a shadow moves, when a comparison becomes possible. Without contrast, motion fades into the feeling of rest. The universe is full of movement that doesn't announce itself, movement that doesn't shake or roar, movement that simply continues quietly at every scale. And you are part of it. Motion in this sense is not something the universe has to maintain. It doesn't need constant encouragement. Once it exists, it tends to remain, which leads to a quiet but important question. If motion comes so naturally, why does anything ever slow down? Why do moving things sometimes come to rest, at least from our point of view? The answer turns out to be less about motion itself and more about what surrounds it. Motion in this sense is not something the universe has to maintain. It doesn't need constant encouragement. Once it exists, it tends to remain, which makes one detail quietly surprising. In our everyday experience, moving things almost always slow down. A rolling ball loses speed. A swinging door comes to rest. Motion feels temporary, as if the world is gently pushing everything towards stillness. But that feeling is shaped by where we live. On Earth, nothing moves in isolation. Air presses back. Surfaces rub against each other. Energy leaks away, not because motion is fragile, but because it is constantly being shared with the environment. What looks like motion fading is really motion spreading out, dissolving into heat, vibration, and sound. If you could remove those interactions, the story would change completely. Imagine an object drifting in deep space, far from planets, far from stars, far from anything solid enough to interfere. If you give it a gentle push, it doesn't slow down. It doesn't tire. It doesn't need fuel. It simply continues carrying that motion forward without preference or intention. This idea can feel unnatural because it goes against what our senses have trained us to expect. We grow up surrounded by friction, so we assume it is universal. But friction is not a rule of the cosmos. It is a local condition. In the vast spaces between stars, resistance becomes so rare that motion can persist for extraordinary lengths of time. Particles travel across galaxies, light crosses the universe itself, not because something keeps pushing them, but because nothing stops them. Stillness in this context becomes the special case. To slow something down, you need interaction, a collision, a force, a way for energy to be transferred elsewhere. Without that exchange, motion has no reason to end. Even when things appear calm, this exchange is often still happening. Energy is always on the move, slipping from one form to another. What changes is not the existence of motion, but where it flows. This is why cooling an object means slowing its internal motion. This is why heat spreads. This is why absolute stillness remains unreachable. As long as there is energy to share, there is motion to distribute. Once you start seeing the universe this way, stillness begins to look less like a fundamental state and more like a temporary balance. A moment where motions cancel out just enough to appear quiet from a distance. And this idea doesn't stop at particles or drifting objects. It scales upward, shaping planets, stars, and entire galaxies in ways that are subtle, persistent, and impossible to fully switch off. Motion doesn't need to be sustained, it needs to be interrupted, and interruptions in the universe are rarer than they first appear. Once you start thinking this way, motion stops feeling like something that happens to objects and starts feeling like something objects are simply made of. Take temperature as an example. We often talk about heat as if it were a substance, something that can be added or removed. But at its core, temperature is a measure of motion. It tells us how energetically particles are moving, how much microscopic activity is packed into a given place. When something cools down, it doesn't lose motion entirely. Its internal motion slows, spreads, and redistributes. Energy flows outward, searching for balance, never quite settling into perfect rest. Even at temperatures close to absolute zero, motion never fully disappears. Quantum effects prevent particles from becoming completely still. There is always a faint restlessness, a baseline activity written into the fabric of reality itself. This means that stillness is not something you reach by slowing things down enough. It is something the universe actively avoids. Now let's widen the view again. Planets follow paths that look stable and predictable, yet those paths exist only because motion is constantly being redirected. Gravity doesn't stop movement. It bends it. It curves straight lines into orbits, turning forward motion into endless loops. Earth does not fall into the sun because it is moving sideways fast enough to miss it over and over again. The moon does not crash into Earth for the same reason. What looks like balance is actually a continuous negotiation between motion and attraction. From far away, these systems appear calm. From close up, they are dynamic, precise, and never static for a single moment. Stars behave in a similar way. Inside them, matter is in constant turmoil. Particles collide, fuse, release energy, and push outward while gravity pulls inward. A star exists because two enormous motions oppose each other just enough to create a long-lived structure. When that balance shifts, the star changes. It expands, it contracts, sometimes it collapses, sometimes it tears itself apart. Motion never stops, it only reorganizes. This pattern repeats everywhere we look. What we call structure in the universe is not the absence of motion, but motion arranged in durable patterns. Swirls, flows, oscillations, and cycles that persist. Not because they are still, but because they are stable. And stability in the universe does not mean frozen. It means continuously moving without falling apart. The more closely we observe the cosmos, the clearer this becomes. Galaxies rotate, clusters drift, vast regions of space slowly stream toward denser areas guided by gravity across unimaginable distances. Nothing is pinned in place, nothing is waiting. Everything is already on its way somewhere else. And yet, from where you are now, listening quietly, it all feels peaceful, almost unmoving. That contrast is not a contradiction. It is the result of scale. Motion can be violent up close and gentle from far away, fast locally and slow across billions of years. The universe does not rush. It unfolds, And as we follow that unfolding to even larger scales, motion begins to blur into something more subtle. Not the movement of objects through space, but the movement of space itself. When motion reaches the larger scale, something curious happens. It stops looking like objects moving through space and starts looking like space itself refusing to stay fixed. On everyday scales, we imagine space as a container, a quiet background where things move around. But as we look farther out, the idea slowly breaks down. Distances between galaxies change even when the galaxies themselves are not actively traveling through space. The universe is expanding, not like an explosion from a central point, but like a stretching fabric. Every region moves away from every other region simply because the space between them is growing. This kind of motion is easy to misunderstand because it doesn't behave like anything we experience in daily life. There is no edge rushing outward, no center to point to. Expansion happens everywhere all at once. Galaxies are carried apart not because they are trying to escape, but because the geometry they exist within is changing. From this perspective, stillness becomes even harder to define. If space itself evolves, then there is no fixed stage where motion can be measured absolutely. Every reference frame is local. Every sense of rest depends on where you choose to stand. Even light, the fastest traveller we know, does not cross a frozen universe. It moves through a space-time that stretches, bends, and responds to energy and mass. Its journey is shaped not only by where it starts and ends, but by how the universe changes along the way. This means that motion is not simply something happening inside the universe. It is something the universe is doing, and once you see that a quiet shift occurs, the question is no longer why things move. The question becomes why anything ever appears stable at all. The answer lies in timescales. Some motions are fast enough for us to notice instantly. Others unfold so slowly that they pass unnoticed over a lifetime. Continents drift. Stars migrate within galaxies. Galaxies themselves rearrange across billions of years. These are motions that feel like permanence only because we are brief. From the universe's point of view, nothing has settled yet. Structures that feel ancient to us are temporary arrangements in a much longer story. They persist not because motion has stopped, but because change is patient. And this patience is what allows the universe to feel calm. It allows you to rest. It allows planets to remain where they are long enough for life to emerge. It allows stars to shine steadily for ages before transforming. But beneath that calm, motion continues, quiet, relentless, uninterrupted. Even now as you listen, the distance between distant galaxies is increasing. Energy is shifting. Space is subtly reshaping itself. Nothing dramatic, nothing sudden. Just the universe doing what it has always done, remaining in motion. And if space itself cannot remain fixed, then stillness is not a destination the universe ever reaches. It is only a perspective we adopt for a moment while everything continues to move beneath us. Take a breath. Let that idea settle gently, because there is one final layer to this story, one that brings motion back home to you, not as an abstract concept, but as something deeply personal. When motion comes back to you, it doesn't arrive as a scientific fact. It arrives as a feeling. Your body is not a solid object resting in a fixed place. It is a system in constant exchange. Air moves in and out of your lungs. Blood circulates. Cells rebuild themselves. Even at rest, your body is a river, not a statue. Every few moments, atoms leave you. Every few moments, new ones take their place. The version of you listening now is not made of exactly the same material as the version of you from a year ago. Continuity does not come from stillness. It comes from flow. This is easy to overlook because the flow is organized. It follows patterns. It maintains form. But form is not the absence of motion. Form is motion that repeats. The same is true far beyond the scale of the human body. Mountains feel permanent, yet they rise and erode. Oceans seem steady, yet they circulate endlessly. Even the solid ground beneath you is slowly shifting, carried by forces deep within the planet. Nothing holds its shape by refusing to move. Things endure by moving in the right way. This is one of the quiet lessons the universe teaches if you take the time to notice it. Stability is not about freezing change. It is about allowing change to happen without breaking the pattern. When something appears still, what you're really seeing is balance. Motions layered on top of motions, cancelling just enough to look calm from a distance. Remove that balance and movement reveals itself again. This is why sudden stillness feels unsettling. A heart that stops, air that no longer flows, energy that no longer circulates. Absolute rest is not peaceful, it is absence. The universe does not drift toward that absence. It moves away from it. Even in decay, motion persists. When stars burn out, their matter spreads. When structures collapse, energy is released and redistributed. Endings are not halts. They are transitions. Seen this way, motion is not something that disrupts order. It is what makes order possible in the first place. Without motion, there would be no mixing, no structure, no evolution, no time for anything to happen at all. And perhaps that is why the universe feels the way it does, vast, slow, and strangely gentle. Not because it is static, but because its motion is measured on scales that dwarf our own. You are carried within that motion, supported by it, sustained by it. You don't need to chase it. You don't need to resist it. It has been moving long before you noticed, and it will continue quietly whether you are watching or not. If motion never truly stops, then rest becomes something else entirely. Not the absence of movement, but a moment where movement no longer demands your attention. Think about how you fall asleep. Your body doesn't shut down. It doesn't power off. It shifts. Breathing slows. Muscles release. Brain activity changes its rhythm. Rest arrives not because motion ends, but because it reorganizes. The universe rests in much the same way. Stars do not pause their internal reactions when they shine steadily. Galaxies do not freeze when their shapes remain recognizable for billions of years. What we call calm is simply motion arranged into long-lasting patterns. This is why the night sky feels peaceful. The stars are moving, but not in ways that rush or collide on human timescales. Their changes are slow enough to feel timeless, even though they are anything but. There is a comfort in that slowness, a reminder that not all motion is urgent. Some movement unfolds so gradually that it creates space for complexity, for structure, for life to exist without being torn apart. The universe learned this balance early on. Too much motion and nothing could settle. Too little and nothing could form. What we see today is the result of countless adjustments guided not by intention, but by the simple rules that allow motion to persist without chaos. This balance is fragile, but it is also resilient. Disturb it slightly and the system adapts. Disturb it greatly and something new emerges. Motion does not vanish. It finds another path. You can see this everywhere once you start looking. In the way storms organize themselves, in the way ecosystems recover, in the way ideas spread, change and return in new forms. Patterns endure because movement continues within them. And this brings us back to the idea that stillness is a perspective, not a property. A choice of scale. A way of looking that smooths over what is too slow, too small, or too vast to notice all at once. From up close, everything is restless. From far away, everything is calm. Both views are true. The universe does not contradict itself. It simply contains more motion than we can hold in a single glance. And as you listen, letting these thoughts drift past without effort, you're doing something very natural. You're aligning with a rhythm that has always been there, slow enough to soothe, steady enough to trust. Because in a universe where nothing ever truly stands still, peace does not come from stopping movement. It comes from moving with it. There is a subtle difference between motion that feels overwhelming and motion that feels supportive. The difference is not speed, it is coherence. When movements align, when they reinforce rather than collide, the result feels stable, predictable, safe. This is true in physics, and it is true in experience. The universe is full of motion that lines, Atoms move, but they bind into molecules. Molecules move, but they assemble into structures. Stars move, but they gather into galaxies that persist for billions of years. At every scale, motion organizes itself into forms that last not by stopping, but by flowing in consistent ways. This is why the universe does not feel chaotic, even though it is never still. Chaos is not movement without rest. Chaos is movement without pattern, and the universe on the largest scales is deeply patterned. You can think of it as a kind of choreography, not planned, not rehearsed, but shaped by simple rules repeated endlessly. Energy flows from dense regions to sparse ones. Matter responds to gravity. Motion follows paths of least resistance again and again. Over time, those paths become familiar. They deepen, they stabilize. From within those paths, everything feels calm. This is also why change can feel sudden to us. When a long-standing pattern breaks, when motion finds a new route, the shift feels dramatic. But even then, nothing has stopped. Motion has simply changed direction. Supernovae do not interrupt the universe's movement. They redistribute it. Collisions between galaxies do not end their journeys. They redirect them. Endings in this sense are not pauses. They are transitions between patterns. Once you begin to see motion this way, fear of change softens. Not because change becomes pleasant, but because it becomes expected, natural, continuous. Nothing is being pushed toward rest. Nothing is waiting to stop. The universe is not running out of motion. It is endlessly rearranging it. And you are part of one of those arrangements. A temporary but meaningful pattern, held together not by stillness but by countless movements working in quiet agreement. Your heartbeat, your breathing, your thoughts drifting as you listen. All of it is motion that has learned how to stay coherent, and for a while that coherence is enough. Enough to feel calm, enough to feel grounded, enough to rest even as everything continues to move. There is one more reason motion feels so natural in the universe, and it has to do with probability rather than force. When there are many possible ways for something to move and very few ways for it to be perfectly still, motion becomes overwhelmingly likely. Stillness is not forbidden. It is simply rare. Imagine a room filled with bouncing particles. Each collision sends them in a new direction. Over time, their paths spread out, explore more space, and become harder to predict in detail. This spreading is not a preference. It is a consequence of numbers. With countless particles interacting, the configurations that involve ongoing motion vastly outnumber the configurations that result in rest. The universe does not choose motion. It drifts toward it because there are more ways to move than to stop. This is where the idea of entropy quietly enters the story. Entropy is often described as disorder, but that description is incomplete. A better way to think about it is as a measure of how many microscopic arrangements correspond to the same overall state. States with higher entropy are simply more probable because there are more ways to realize them, and most of those ways involve motion. Energy spreads, momentum disperses, differences even out. Not because the universe is trying to erase structure, but because movement naturally explores what is available. This does not mean the universe is falling apart. As energy spreads, it also creates gradients, and gradients drive motion in new directions. Heat flows from hot to cold. Matter falls toward dense regions. Motion gives rise to more motion. Seen this way, stillness would require an extraordinary level of coordination. Every particle would need to cancel every other movement perfectly all at once. The odds of that happening are so small that for all practical purposes it never does. What we experience as rest is simply motion averaged out, so many tiny movements layered together that from a distance they appear smooth and unchanging. This statistical view of the universe can feel impersonal, but it leads to a comforting realization. The universe does not need to be driven. It does not need constant input to remain active. Activity is the natural outcome of its complexity. And because of that, motion does not have to be fast to be meaningful. It does not have to be dramatic to be real. Even the quietest systems are alive with change beneath the surface. The universe keeps moving not because it is restless, but because it is rich with possibilities. And within that richness, stillness remains what it has always been, a fleeting appearance created when countless motions happen to balance out just long enough for us to call it calm. At this point, it helps to notice something subtle about how we talk about motion. We often describe it as if it belongs to individual things. This particle moves, that planet travels, this galaxy drifts. But in reality, motion is rarely owned by a single object. It belongs to relationships. An object is only moving relative to something else. Without a reference, the word motion loses its meaning. There is no universal marker that says this is the place of rest. You can feel still inside a moving car. You can feel motionless on a rotating planet. You can even feel calm inside a system that is changing rapidly. As long as everything around you changes together, the universe offers no absolute frame where motion can be measured once and for all. Every sense of rest is local, temporary, contextual. This is why two observers can disagree about what is moving and still both be correct. One may see a spacecraft racing past. Another inside the craft may feel perfectly at rest. Neither perspective is privileged. Motion depends on where you stand. Once you accept this, stillness becomes even harder to pin down. If rest is always relative, then the idea of something being truly motionless loses its footing. There is always another frame, another scale, another point of view where movement reappears. Even the universe as a whole does not provide a fixed background. Space expands, time stretches, distances evolve. The coordinates themselves refuse to remain static. So when we say that nothing ever truly stands still, we are not making a dramatic claim. We are acknowledging a limitation, not of the universe, but of the concept of stillness itself. Stillness is something we assign. Motion is something that persists. This can feel unsettling at first, as if the ground beneath certainty is always shifting, but it can also be freeing. If rest does not depend on the universe stopping, then peace does not require motion to end. You can be at rest while moving. You can feel calm while change continues. You can exist within a flow without being overwhelmed by it. The universe demonstrates this constantly. Systems endure not by freezing themselves in place, but by remaining flexible, by allowing motion while keeping relationships intact. And that is perhaps the most useful way to think about motion, not as something to escape, but as something to be held in balance. Because if motion is everywhere, then rest is not found by seeking a place where nothing moves. It is found by finding a frame where movement becomes gentle enough to live within. And that frame does not have to be cosmic. It can be as small as this moment, as simple as listening. There is a quiet irony hidden in all of this. The more deeply we understand motion, the less threatening it becomes. At first, motion sounds like instability, like change that cannot be controlled. But in practice, motion is what allows predictability to exist at all. Without it, there would be no cycles, no rhythms, no repeating patterns for the universe to lean on. Day follows night because Earth keeps turning. Seasons return because Earth keeps moving. Stars shine steadily because internal motions remain balanced over long stretches of time. If motion were absent, there would be no regularity, only sudden beginnings and abrupt ends. Instead, the universe chooses continuity through movement. This continuity is subtle. It doesn't announce itself. It doesn't insist on being noticed. It simply persists, providing a stable background against which change can happen gradually rather than all at once. This is why so much of the universe feels predictable, even though it is never still. Motion smooths itself out over time. Small fluctuations cancel, large patterns dominate. What remains is a slow, dependable flow. From within that flow, it becomes possible to plan to adapt to exist without constant surprise. Life depends on this, not because life requires stillness, but because it requires motion that doesn't break its own rules, motion that stays within certain bounds, motion that repeats often enough to be learned. Your own body reflects this perfectly. Your heart beats not once but again and again, with small variations that never quite repeat, yet never drift too far. Breathing follows a similar pattern. So does sleep, so does thought. These are not static states. They are moving equilibria. When they are disrupted, discomfort appears, not because motion has returned, but because it has lost its familiar structure. Rest, then, is not the absence of motion, but the presence of reliable motion. The universe seems to understand this instinctively. It favours processes that unfold steadily. It allows extremes, but it does not linger in them. Explosions are brief. Collapse is rapid. What remains afterward is slower, calmer, and more enduring. This preference is not intentional. It is statistical. States that persist are the ones that last long enough to be observed. States that do not persist vanish before they can leave much behind. Over time, this shapes what the universe looks like. Not chaotic, not frozen, but gently active. And within that activity there is room to pause. Not because motion stops, but because it becomes predictable enough to feel safe. As you listen now, nothing around you is truly settled. The planet continues its turn. The air continues its flow. Time continues its quiet advance. Yet you can rest anyway. Because rest was never about stopping the universe. It was about finding a place within its motion where you don't need to fight it. There is another way to see motion that makes it feel even less abstract. Instead of asking how fast things move, ask how often they change. Change is the true marker of motion. And change does not require speed. It only requires time. A glacier moves more slowly than almost anything we can observe directly. Yet it reshapes landscapes. It grinds mountains into valleys. Over long enough periods, its motion becomes undeniable. Not because it rushed, but because it never stopped. The universe is full of glaciers like this. Processes so slow that they appear frozen until you zoom out far enough in time to see their paths etched clearly across reality. Stars evolve this way. They spend most of their lives appearing constant, their light steady, their size unchanged. But inside, fusion gradually alters their composition. Over millions and billions of years, that quiet motion transforms them completely. Galaxies behave similarly. From one human lifetime to the next, their shapes seem fixed. But over cosmic time, they drift, stretch, collide, and merge. Their apparent stillness is a consequence of our short perspective, not their true nature. This teaches us something important about motion. It does not have to announce itself to be real. It does not need to be visible to be present. Motion can be patient, and patience changes how we experience it. When motion is fast, we brace. When motion is slow, we adapt. The universe on its largest scales moves slowly enough for complexity to grow without being torn apart. This slowness is not accidental. Systems that change too quickly rarely last. They burn out, they collapse, they scatter. What remains are the motions that learned how to stretch themselves across time. This is another reason stillness feels common. Not because motion is rare, but because the motions that survive are the ones gentle enough to endure. And endurance shapes perception. When something lasts long enough, we treat it as permanent. When change is subtle enough, we call it rest. But permanence in the universe is only long-lived motion viewed from the inside. Even the laws that govern motion seem steady only because they apply consistently. They do not halt change, they guide it. This is why the universe can feel both dynamic and calm at once. Why it can be endlessly active without becoming overwhelming. Motion is everywhere, but it is not in a hurry. And neither are you required to be. You are allowed to exist at your own pace, nested within motions far larger and far slower than anything you need to manage. The universe is not rushing you forward, it is carrying you along. As these ideas settle, notice how they don't demand attention. They don't ask you to remember equations or definitions. They simply offer a different way of seeing what has always been there. Nothing stands still, but nothing needs to rush. And somewhere between those two truths, a quiet sense of balance emerges. When you hold all of this together, a different picture of the universe begins to form. Not a place filled with things that occasionally move, but a place where movement is the default condition, and form is what briefly emerges from it. This reverses a very old assumption. We tend to think of objects first and motion second. A planet exists, then it moves. A star forms, then it changes. But in reality, motion often comes first. Objects are what motion looks like when it becomes organized. A whirlpool in a river is not a separate thing added to the water. It is the water moving in a particular pattern. As long as that pattern holds, the whirlpool appears stable. When the flow changes, it disappears without leaving a trace. Many structures in the universe work the same way. A star is not a static ball of matter. It is a continuous process maintained by inward and outward motions balancing each other. A galaxy is not a rigid structure. It is a long-lived swirl of matter, energy, and gravity slowly reshaping itself as it turns. Even solid objects are less solid than they appear. Their rigidity comes from electromagnetic forces constantly pushing particles apart, holding them in place relative to one another. What feels firm is actually dynamic equilibrium. Seen this way, stillness is no longer something to look for. It is something that appears when motion becomes self-consistent, when change happens in a way that preserves shape. This also explains why the universe can change without feeling unfamiliar. The patterns evolve, but they do so smoothly. Gradually, one arrangement flows into another without sharp boundaries. There is no universal pause button between these transitions, no moment where motion stops and something new begins. Everything overlaps, everything blends, and this continuity is what makes the universe feel inhabitable. Sharp, absolute changes would be impossible to live within, but slow motion layered over vast spans of time allows complexity to arise without being destroyed by it. You are an example of this. Your life is not a series of disconnected moments. It is a continuous flow where each state grows out of the one before it. Even rest is part of that flow, not an interruption. This is why the universe does not need stillness to be stable. It needs coherence. It needs motion that doesn't tear itself apart. And when coherence holds motion becomes gentle, predictable, almost invisible, that invisibility is what allows us to forget how much is happening beneath the surface, to feel calm even as the universe continues its quiet work. Nothing stands still, but much of it moves in ways that are kind. Let that idea linger for a moment. There's no need to resolve it quickly, because the universe is not finished moving, and neither is this story. There is a moment when this idea settles in not as information but as perspective, when motion stops feeling like something happening out there and starts feeling like the quiet condition of being. If nothing ever truly stands still, then the universe is not something we occasionally disturb by moving through it. We're already woven into its movement from the beginning. There was never a moment of rest before motion began. There was only motion arranging itself into forms that could last. This is true even at the beginning of cosmic history. The early universe was not a static point waiting to explode. It was already active, already changing, already expanding and cooling at the same time. From its first moments, motion was not added later. It was present from the start. As the universe expanded, motion did not fade. It diversified. Energy spread out. Matter clumped together. New kinds of movement emerged layered on top of the old ones. Rotation, vibration, flow, expansion. Each scale inherited motion from the one before it. And through all of this, there was no universal reference for rest. No frame you could step outside of and say, here, finally everything is still. Every attempt to define such a frame dissolves into relativity. Rest always depends on where you stand and what you compare yourself to. This is why stillness feels so fragile. The moment you shift perspective, it vanishes. But fragility does not mean insignificance. Stillness has meaning because it is local, temporary. It gives structure to experience even if it does not describe the universe as a whole. A lake can look perfectly calm while currents move beneath its surface. A city can feel quiet at night while millions of systems continue to function. A mind can feel at rest while thoughts drift slowly in the background. These moments are real. They matter. They just don't require motion to end. The universe seems to offer this kind of rest generously, not by stopping its movement, but by stretching it across scales so vast that from within them everything feels slow enough to breathe. That may be why the night sky invites stillness. Not because it is inactive, but because its motion is spread so thin across time that it no longer presses on us. When you look up, you are not seeing a frozen scene. You're seeing a long exposure of countless movements layered together. A record of change that has learned how to feel calm, and perhaps that is the deepest lesson hidden in all of this. Stillness is not something the universe achieves by ending motion. It is something we experience when motion becomes wide enough, slow enough, and gentle enough to hold us without effort. You don't have to escape movement to find rest. You only have to stop resisting it. As everything continues its quiet drift, atoms, planets, galaxies, space itself, you're allowed to drift too. Not aimlessly, not urgently, just enough to stay part of the flow. Nothing in the universe ever truly stands still, and somehow within that truth there is room to rest. One reason motion feels confusing is that we rarely experience it directly. Most of the time what we experience is filtered motion. Your senses are not designed to detect every movement around you. They are designed to detect changes that matter for survival. Slow motion fades into the background. Balanced motion disappears entirely. Only differences register. This is why you can feel perfectly still inside a moving vehicle. Your body, the seat, the air around you, all of them share nearly the same motion. With nothing to compare against, your nervous system labels the situation as rest. The universe behaves the same way. Motion becomes noticeable only when it creates contrast, a sudden acceleration, a collision, a shift relative to a nearby reference. Without contrast, motion continues unnoticed even when it's enormous. This is not a flaw in perception. It is a necessity. If the brain tried to track every motion at every scale, it would be overwhelmed instantly. Instead, it builds a simplified picture of reality, one where motion is ignored unless it breaks a pattern. Stillness, then, is not something we observe, it is something we construct. We define rest by choosing a frame of reference and holding onto it. Earth becomes our default. The room becomes our anchor. Anything moving with us feels still. Anything moving differently stands out. This process is so automatic that we forget it is happening. We speak as if rest were an objective state, when in reality it depends entirely on context. Once you notice this, an important question emerges. If stillness is defined locally and motion depends on comparison, then how do scientists talk about motion at all? The answer lies in measurement. To study motion physics does not ask whether something is truly still. It asks how something changes relative to a chosen frame, velocity, acceleration, rotation. All of these require reference points. Without them, the concepts lose meaning. There is no universal ruler fixed to the universe. No cosmic floor where everything else moves on top. Every measurement begins by declaring, often implicitly, what will count as at rest. This is not a limitation of physics. It is a reflection of how motion actually works. And once motion is understood this way, the idea of the universe needing a final state of rest begins to dissolve. There is no privileged position where movement stops. Only countless local frames, each internally calm, each embedded within larger flows, which leads to a deeper and more practical question. If absolute stillness does not exist, why does the universe contain so many stable structures? Why do planets keep their orbits? Why do atoms hold together? Why does anything persist long enough to be recognizable? The answer is not that motion disappears. It is that motion becomes constrained. Constraint is the missing piece that turns motion into structure. Free motion spreads endlessly. Constrained motion repeats. When forces limit how movement can unfold, patterns emerge, orbits form, vibrations settle into frequencies, particles bind into atoms. Systems become predictable not because motion ends, but because its possibilities narrow. This is why stability does not require rest. It requires boundaries. An atom is stable because electrons are confined to specific states. A planet's orbit is stable because gravity restricts its path. A star shines steadily because inward and outward motions remain locked in a long-term balance. Remove the constraints and motion escapes. Matter disperses, energy spreads, structure dissolves. But as long as constraints hold, motion continues inside them, endlessly cycling without destroying the system. This is why the universe appears filled with long-lived forms. Not because it has slowed down, but because many motions have learned how to stay contained. And containment does not freeze motion, it organizes it. This idea scales upward again and again, from atoms to molecules, from planets to solar systems, from galaxies to clusters. Each level introduces new constraints shaping motion into larger, slower patterns. The universe does not pause between these levels. There is no reset. Motion passes upward, becoming more structured, more layered, more durable. Stillness from this perspective is simply motion that has found a narrow path to follow. And once you see that, the question shifts again, not toward meaning or rest, but toward mechanism. What kinds of constraints exist at the larger scales? How does motion remain organized across billions of years? And what happens when those constraints finally fail? Those questions are where the story continues. Once motion is constrained, the next question becomes unavoidable. What determines how long those constraints last? Some constraints are incredibly resilient. Atomic bonds can persist for billions of years. Planetary orbits can remain stable longer than the lifetime of stars. Others are fragile, holding only briefly before breaking apart. The difference is not intention or design. It is energy flow. Every constraint exists within an environment. Energy enters, energy leaves. As long as that exchange stays within certain limits, the structure survives. When it doesn't, the constraint weakens and motion finds new paths. This is why stability is never absolute. It is conditional. Take a planet in orbit. Its motion is constrained by gravity, but that constraint is not eternal. Gravitational interactions with other bodies slowly alter the orbit. Energy is exchanged, redistributed. Over long enough timescales, even the most stable paths change. The same principle applies everywhere. Atoms can be ionized. Molecules can break apart. Stars eventually exhaust the processes that keep their internal motions balanced. Constraints fail not because motion disappears, but because it overwhelms the boundaries that once shaped it. This perspective helps explain something that often feels counterintuitive. The universe can be filled with stable structures and still be fundamentally dynamic. Stability is not a pause in motion. It is a temporary agreement between competing movements. As long as that agreement holds, the system appears calm. When it fails, change accelerates. This is also why time matters so much when talking about motion. On short time scales, constraints feel solid. On longer ones, they reveal their limits. What looks permanent within a lifetime may be fleeting on cosmic scales. Physics handles this by never assuming eternal rest. Instead, it tracks how systems evolve under constraints and how those constraints shift over time. Motion is always present. The only question is how it is being shaped at any given moment. Seen this way, the universe is not divided into moving things and resting things. It is divided into regions where motion is tightly regulated and regions where it is free to spread. And this division is not fixed. Regions of constraint form, persist, and dissolve. New ones emerge elsewhere. Motion migrates from one pattern to another, carrying energy forward through an endless sequence of reorganizations. This is why the universe does not need a final state of rest to make sense. It only needs rules that determine how motion flows and where it can linger. Which brings us to a deeper issue. If motion is always present and constraints merely guide it, then what determines the direction of change? Why do systems tend to move from tightly constrained states toward more distributed ones? Why does motion seem to spread rather than concentrate over time? Answering that requires looking not at individual systems but at the overall tendency of motion itself. And that tendency becomes clearer when we talk about time not as a background but as something shaped by motion. When we talk about the direction of change, it's tempting to imagine some built-in arrow guiding the universe forward, but there is no external guide, no instruction telling motion where to go next. The direction comes from statistics. When motion is constrained, there are only a few ways it can move. When constraints weaken, the number of possible motions increases dramatically. Systems don't move toward these states because they are better or more complete, but because there are simply more of them. This is why motion tends to spread. A tightly constrained system is rare. It represents a very specific arrangement of energy and matter. A loosely constrained system can be realized in countless different ways. Over time, small fluctuations push systems towards states that are easier to occupy, not because they are preferred, but because they are abundant. This is the practical meaning behind the arrow of time. Time does not flow because the universe is moving forward towards something. It flows because systems naturally drift from less probable arrangements to more probable ones. Motion explores what is available, and what is available grows as constraints loosen. Importantly, this does not mean that order immediately collapses. Constraints can persist for extraordinary lengths of time. What matters is not speed, but tendency. Given enough time, even rare transitions become inevitable. This is why physics rarely asks whether a system will change, but how long it will take. Some changes happen quickly, others unfold so slowly that they appear frozen. Both are expressions of the same underlying rule. Motion continues and probability shapes its path. From this perspective, time is not a force acting on the universe. It is a way of describing how motion reorganizes itself as constraints shift. The forward direction of time is simply the direction in which more arrangements become accessible. Nothing is pushing the universe forward. Nothing is pulling it toward rest. Motion is just moving where it has room to go. This also explains why reversing large-scale motion is so difficult. To do so, you would need to guide a system back into a narrower set of arrangements coordinating countless small motions simultaneously. At small scales, this can happen briefly. At large scales, it becomes overwhelmingly unlikely, which means that stillness is not only rare but fragile. It can exist locally, it can exist temporarily, but it cannot dominate. And this fragility is not a flaw. It is what allows the universe to keep evolving without becoming trapped in any single configuration. As constraints relax and motion spreads, new structures form elsewhere. New balances emerge. The universe does not move toward uniformity all at once. It redistributes complexity, shifting it from one region to another. Understanding this makes motion feel less like a blur and more like a process. One that can be followed, described and predicted within limits. And those limits matter, because while motion tends to spread, it does not do so uniformly. Some regions remain ordered far longer than others. Some systems resist change with remarkable persistence. Explaining why those regions exist and how they manage to last requires looking more closely at how motion interacts with information, not just energy. That's where the story continues. When motion is discussed only in terms of energy, something important gets missed. Energy tells us how much movement exists. Information tells us how that movement is arranged. Two systems can contain the same amount of energy and behave in completely different ways. One may look chaotic and short-lived. The other may remain structured for a very long time. The difference is not energy itself, but how much information is encoded in the system's motion. Information in physics is not about meaning or messages. It is about specificity, about how tightly constrained a system's possible states are. A system with high information has fewer ways it can move without losing its identity. A system with low information can change in many ways and still be considered the same. This is why certain structures endure. A crystal persists because its internal motion is highly constrained. Atoms vibrate, but only within very specific positions. A planet remains recognizable because its orbit restricts how its motion can evolve. A living organism survives because biochemical processes channel motion into narrow, repeatable pathways. None of these systems are still. They are informationally organized. What motion tends to erase over time is not energy but information. As constraints weaken, the number of accessible states grows, and specific arrangements become harder to maintain. This is why entropy is often described as a loss of information rather than a gain of disorder. Seen this way, the universe is not simply spreading motion. It is gradually reducing the amount of information required to describe large-scale systems. This does not happen everywhere at once. Locally, information can increase. Stars form, planets assemble, life emerges. These processes concentrate motion into highly specific arrangements, but they do so by exporting entropy elsewhere. They rely on gradients, on differences, on motion flowing through them. So while motion tends to spread globally, it can still be organized locally as long as there is somewhere for excess motion to go. This is why long-lived structures are always open systems. They exchange energy and matter with their surroundings. They maintain information by constantly processing motion, not by isolating themselves from it. Complete isolation would eventually erase structure. Perfect stillness would destroy information entirely. From this perspective, motion and information are inseparable. Motion provides the activity, information provides the shape. Remove either, and nothing recognizable remains. This helps explain why the universe contains islands of order within an overall trend towards spreading. Those islands are places where motion is temporarily guided, filtered, and recycled in ways that preserve specific patterns. But temporary is doing a lot of work here. Even the most information-rich systems are not permanent. Their constraints erode, their channels leak. Over long enough timescales, the motion they organize escapes into broader distributions. The universe allows structure, but it does not guarantee its preservation. Which raises a careful question. If motion naturally erodes information over time, why does the universe keep producing new structures at all? Why doesn't everything simply flatten out as soon as it forms? Answering that means looking at where motion comes from, not just how it spreads and why the universe never runs out of it. It might sound reasonable to say that motion explains change, but in many cases the opposite is true. Change is what reveals motion. If nothing ever changed, no positions, no states, no relationships, motion would be physically meaningless. You could assign a speed, a direction, a vector, but none of it would be observable. Motion only becomes real when something ends up different from how it began. This matters because it forces us to be precise. Motion is not defined by how fast something goes. It is defined by what changes over time. And this is where a common misunderstanding appears. We often imagine that motion must be smooth and continuous, but many of the most important motions in the universe are not. They happen in steps, in jumps, in discrete transitions that only look smooth when averaged over large numbers. At the microscopic scale, particles do not glide gracefully from one state to another. They switch. They occupy one configuration, then another. What we call motion is the accumulation of those transitions. The same idea appears at larger scales. A planet does not move because it is constantly falling smoothly through space. It moves because moment by moment its position relative to other bodies changes. Those changes follow constraints, but they are still changes. This distinction becomes crucial when we talk about stillness. A system can be full of motion and still appear unchanged. Another system can barely move and yet transform completely. The difference is not speed, it is sensitivity. If a system's motion does not alter its observable state, we describe it as stable. If small motions accumulate into visible change, we describe it as dynamic. Stillness then is not about motion being absent. It is about motion being insufficient to matter at the scale we're observing. This is why motion can hide so effectively. At one scale, atoms vibrate without altering the shape of an object. At another scale, continents drift slowly enough that coastlines feel permanent. In both cases, motion exists. It simply fails to cross the threshold of noticeable change. Physics handles this by separating motion from effect. It asks not only how things move, but what that movement does. Does it alter structure? Does it transfer energy? Does it modify constraints? Only when the answer is yes do we say something has changed. This reframes the problem completely. The universe does not contain moving things and still things. It contains processes that matter at certain scales and processes that don't. Motion is everywhere. Change is selective, and this selectivity is not arbitrary. It is governed by thresholds, limits beyond which accumulated motion becomes irreversible, observable, and meaningful. Understanding those thresholds is essential because they determine when motion stays hidden and when it reshapes the world. Once we start paying attention to thresholds instead of speed, a new question becomes unavoidable. What determines when motion crosses that line? When does quiet activity become visible change? That question does not lead toward rest or resolution. It points to instability not as a failure but as a condition the universe carefully avoids crossing too often. Most systems do not sit at equilibrium. They hover near it, and understanding why they stay there requires looking at what happens when motion begins to amplify instead of cancel out. Instability begins when motion stops cancelling out and starts reinforcing itself. In many systems, small deviations are harmless. A particle drifts slightly, a planet's orbit wobbles, a temperature fluctuates. As long as opposing processes push back, those deviations fade. Physicists call this negative feedback. It is what keeps motion contained, but not all feedback is negative. Sometimes a small change makes the next change more likely. Motion feeds motion. Energy concentrates instead of spreading. This is positive feedback, and it behaves very differently. A tiny imbalance grows. A fluctuation amplifies. Motion accelerates instead of smoothing out. This is how calm systems become unstable. You can see this clearly in simple cases. Heat rising in air normally diffuses away. But if warmer air keeps rising and cooler air keeps sinking, circulation strengthens. A gentle gradient turns into convection. Push it further and turbulence appears. The same logic applies far beyond everyday scales. Inside stars, nuclear reactions create outward pressure. Gravity pulls inward. As long as these motions counterbalance, the star remains stable. But if pressure drops or gravity gains the upper hand, motion no longer cancels. Collapse accelerates. The system reorganizes rapidly. Instability is not motion appearing where there was none. It is motion escaping its constraints. This distinction matters because it explains why the universe does not constantly tear itself apart. Most systems are dominated by negative feedback. Deviations are damped. Motion is recycled into predictable paths. Positive feedback exists, but it is rare, localized, and usually short-lived. When it appears, change is sudden and dramatic. When it ends, the system settles into a new regime where constraints reassert themselves. From a distance, this can look like the universe alternating between calm and violence. But underneath, the same rules apply. Motion is always present. What changes is whether it is being regulated or allowed to run free. This also explains why instability feels directional. Once positive feedback takes hold, reversing it becomes difficult. Motion has momentum not just in speed, but in structure. The system moves away from its previous state because returning would require coordinating many independent motions at once. Most of the time, that coordination never happens. Instead, the system finds a new balance. New constraints form. Motion becomes organized again, though not in the same way as before. This cycle, constraint, fluctuation, instability, reorganization, repeats across the universe. It is not an exception. It is a fundamental pattern, and crucially, it does not require motion to stop at any point. Even during the most violent transitions, motion is continuous. Only its structure changes, which brings us back to stillness. If stillness were a real absolute state, instability would be impossible. There would be nothing to amplify, nothing to escape. The fact that instability exists at all is evidence that motion never truly disappears. It only waits constrained until conditions allow it to reshape the system. Understanding where those conditions come from and why some systems hover near instability without crossing it requires looking at how motion is regulated over time, not just in space. That regulation is subtle. It depends on delays, thresholds, and response times, and those details matter more than speed ever does. One reason instability is so rare is that motion does not respond instantly. Every system has delays. When something changes, the response takes time to propagate. Forces travel, signals move, energy redistributes. During that delay, motion can accumulate without immediately triggering correction. These delays are small in some systems and enormous in others. In a solid object, forces travel quickly. Disturb it and restoring motion appears almost immediately. In a planet-sized system, responses take much longer. In a galaxy, the delay can span millions of years. This matters because feedback only works if it arrives in time. Negative feedback stabilizes a system only when the response outruns the disturbance. If the correction arrives too late, motion overshoots. The system doesn't gently return to balance. It swings past it. This is how oscillations form. A pendulum is not stable because it stops moving. It is stable because its motion repeats. Energy flows back and forth between forms delayed just enough to prevent collapse, but not enough to escape entirely. Many systems in the universe behave like pendulums on vastly different scales. Stars pulse, orbits precess, climate cycles repeat. These are not signs of instability. They are signs of delayed regulation. Motion is not eliminated. It is timed. When delays grow too large, oscillations stop being gentle. They grow. What was once a cycle becomes runaway behavior. At that point, the system reorganizes, often violently. But notice what determines the outcome, not the amount of motion, the timing of its response. This is why fast systems can be stable, while slow systems become unstable, and why some massive structures endure for billions of years while others collapse suddenly. The universe is not sorting systems by how much they move. It is sorting them by how well motion is regulated across time. Stillness, once again, is not the goal. Synchronization is. When responses align with disturbances, motion stays bounded. When they fall out of step, motion escapes. This explains something subtle about why the universe feels predictable at human scales. Most of the systems we interact with have response times tuned to our experience. They correct quickly enough to feel solid, slow enough to feel smooth, but zoom out far enough and that tuning disappears. On cosmic scales, responses lag behind causes by enormous margins. What looks stable now may already be unstable, simply waiting for its correction to arrive too late. This does not make the universe fragile. It makes it patient. Motion unfolds. Delays accumulate. Responses arrive. Patterns shift. And at no point does anything need to come to rest. What matters is whether motion remains coordinated across the timescales involved. Understanding that coordination and how it breaks is essential, because it determines not just when systems change, but how abruptly they do so. That distinction becomes especially important when we look at the largest systems of all, where delays stretch longer than the age of life itself. Many instabilities do not begin because motion grows too strong. They begin because different parts of a system stop agreeing on how fast change should happen. Every complex system contains multiple timescales layered on top of one another. Some processes react quickly, others respond slowly. Stability exists only while those layers remain compatible. When they drift apart, motion stops being coordinated. You can see this in simple systems. A bridge can handle steady winds, but if gusts arrive at just the wrong rhythm, oscillations build instead of fading. Nothing about the wind becomes stronger. The problem is timing across scales. The universe works the same way. Inside a star, nuclear reactions respond to pressure almost instantly. Gravity acting across the entire mass responds more slowly. As long as those timescales stay aligned, the star remains stable. When they drift apart, equilibrium breaks. At galactic scales, the mismatch becomes extreme. Stars respond to local gravity quickly. Entire galaxies respond to large-scale gravitational fields slowly. Between those two layers, motion can build quietly for millions of years before anything visibly changes. This is why large systems often appear stable right up until they aren't. Instability is not always preceded by warning signs. Motion accumulates in places that respond slowly, while faster parts of the system adapt and mask the imbalance. By the time the slow layers react, the system has already crossed a threshold. From the inside, this feels sudden. From the outside, it was inevitable. This is another reason stillness is misleading. A system can look calm because its fastest processes are well regulated, even while slower processes drift out of alignment beneath the surface. Nothing has stopped moving. Motion has simply become asynchronous. Physics describes this in many different ways depending on context, but the underlying idea is the same. Stability requires not just constraints, feedback, and delays, but compatibility across scales. When motion at one scale demands a response that another scale cannot provide in time, the system reorganizes. And that reorganization does not restore the previous stillness. It creates a new pattern with new constraints and new timescales. This is why the universe is filled with structures that look long-lived but not eternal. They persist only as long as their internal clocks remain synchronized. Once they drift apart, motion finds a new arrangement. This helps explain why nothing ever truly settles into a final state. Even if motion is tightly constrained at one level, it is still embedded within larger systems that evolve on longer timescales. Eventually, those larger motions matter. The universe does not collapse into chaos all at once. It reorganizes one scale at a time, and because those scales are stacked so deeply, the process feels slow, predictable, and almost still until you widen your view. That widening is unavoidable, because every system, no matter how stable it appears, is part of something larger that moves on a different clock, and that difference is enough to keep motion alive. There is a final complication that quietly shapes how all of this appears to us. We never observe motion directly. We observe it through instruments, clocks, and comparisons that have limits of their own. Every measurement has a resolution, a smallest interval it can distinguish, a shortest time it can resolve. Below that threshold, motion does not disappear. It becomes invisible. This matters because much of the universe's motion happens either too slowly or too subtly to register at human scales. We call something stable not because it lacks motion, but because our tools cannot resolve the changes it undergoes. A mountain appears immobile because its deformation rate is far below what a human lifetime can track. A galaxy appears frozen because its internal rearrangements unfold over hundreds of millions of years. Even atomic motion becomes still if you average it long enough. Physics accounts for this by choosing scales deliberately. It decides which motions matter and which can be averaged away. Thermodynamics ignores individual particles. Orbital mechanics ignores atomic vibration. Cosmology ignores planetary detail. None of these choices are wrong, but all of them hide motion. This is why the universe feels layered. At each scale, some motions are emphasized and others are suppressed. What looks like rest at one level is often intense activity at another. Stillness, then, is not a property of systems. It is a property of descriptions. We decide what counts as motion by deciding what we are willing to measure. Everything else becomes background. This is not a weakness of science. It is what makes understanding possible at all. Without abstraction, the universe would be unreadable. But abstraction comes with a cost. It smooths reality until motion feels optional. Once you notice this, a pattern emerges. Whenever we say something is not moving, what we really mean is that its motion does not affect the questions we are asking. Change is present but irrelevant at that level of description, and relevance is always contextual. This explains why the same system can be described as stable in one theory and dynamic in another without contradiction. Each theory is filtering motion differently based on scale, purpose, and precision. The universe does not care which description we choose. Motion continues regardless. What changes is only how much of it we allow ourselves to see. As we widen our measurements, refine our clocks, and extend our observations across longer spans of time, motions once thought negligible become dominant. What felt permanent becomes provisional. What felt still becomes active. This is not a failure of earlier understanding. It is the natural consequence of looking more closely, and it reinforces the central idea in a very practical way. Nothing in the universe ever truly stands still. Not because motion is dramatic, but because it never fully drops below zero. It simply falls below our threshold of notice. That threshold moves. Our instruments improve. Our perspective widens. And with each step, stillness retreats a little further, revealing motion that was always there waiting to be seen. Consider a system that feels as close to stillness as anything we know, a cold, dark region of space far from stars where matter is sparse and temperatures are low. At first glance, nothing seems to be happening there. No light is produced. No objects collide. No obvious change unfolds. It looks like motion has finally faded to near zero. But even here, motion has not vanished. Gas particles drift slowly, pulled by faint gravitational gradients. Radiation passes through, carrying energy from distant events. Magnetic fields fluctuate. Quantum effects prevent particles from settling into perfect rest. The region evolves not dramatically but continuously. What makes this example useful is not that it is extreme, but that it removes many distractions. With most interactions stripped away, what remains is motion in its most reduced form. And even then it persists. Over long periods of time, that slow drift matters. Slight density differences grow. Matter accumulates. Eventually, the region no longer remains dark. A cloud forms. Gravity strengthens. Motion becomes more organized, not because something new was added, but because existing motion found a way to concentrate. This is how stars begin. Nothing turns on motion to start the process. There is no trigger that breaks stillness. The system was never still to begin with. It was only moving too quietly to notice until the conditions aligned. This pattern repeats everywhere. What we label as beginnings are usually thresholds, points where accumulated motion becomes visible. What we label as endings are points where motion disperses below our ability to track it. In neither case does motion appear or disappear. This reframes how we should think about the universe's most dramatic events. Star formation, galaxy collisions, cosmic expansion. These are not interruptions of calm. They are moments when underlying motion crosses a scale that matters. And because scale is relative, what counts as happening depends entirely on perspective. From close up, a forming star is chaotic. From far away, it is just a slow brightening. From a cosmic viewpoint, it is a minor rearrangement in a vast flow of matter. Stillness exists only in the gaps between these perspectives. The same is true closer to home. A room feels quiet, not because nothing moves, but because nothing changes fast enough to demand attention. Air currents cancel, temperatures equalize, sounds decay, motion smooths itself out. This smoothing is not an end state. It is a temporary balance. If energy enters the room, motion reorganizes again. If gradients form, flows return. Nothing has to be restarted. Motion never left. Understanding this makes one thing clear. The universe does not need events to stay active. It does not wait for triggers or interventions. It evolves continuously whether or not the changes are obvious. What we experience as calm is simply motion operating below the level of disruption. And that is why the idea of absolute stillness remains elusive. Not because it is forbidden by some law, but because even the quietest systems continue to change, however slowly. Motion does not require drama. It only requires time. At this point, it helps to confront a very common intuition directly. If motion never stops, then why does the universe sometimes look like it is running down? We see stars burn out. We see systems lose energy. We talk about cooling, fading, and eventual darkness. This sounds like motion disappearing. But what is actually happening is redistribution. When a system loses energy, it does not lose motion. It transfers motion to places where it becomes harder to use. Heat spreads into colder regions. Radiation escapes into space. Energy becomes more evenly distributed, not absent. From the system's point of view, useful motion is gone. From the universe's point of view, motion has simply changed address. This distinction matters because it explains why decay and motion are not opposites. Decay is motion becoming less concentrated, less structured, less able to drive organized change. A fire goes out, not because motion stops, but because thermal motion spreads into the environment until no temperature difference remains to sustain combustion. The particles are still moving. They are just no longer moving in a coordinated way that matters locally. The same principle applies at cosmic scales. A star stops shining when nuclear reactions can no longer maintain the gradients required to support them. Motion continues inside the remnant, but the pathways that once shaped it have collapsed. Energy leaks away instead of cycling back into structure. This is why physics distinguishes between motion and free energy. Motion can persist indefinitely. Free energy cannot. Once gradients flatten, motion loses its ability to do work. Stillness again is not the end result. Equilibrium is. An equilibrium is not a state of rest. It is a state where motion no longer produces change at the scale of interest. This is a crucial difference. The universe may approach equilibrium in some respects, but it never reaches a point where particles stop moving. Fields stop fluctuating, or space-time itself becomes inert. What changes is the effect of motion, not its existence. This helps clarify a misconception about the universe's future. Predictions of heat death are not predictions of stillness. They are predictions of uniformity, a state where motion persists but lacks direction, contrast, and leverage. Even then, motion does not vanish. It becomes evenly spread, statistically balanced, and observationally quiet, which means that even the far future of the universe, whatever form it takes, will not be a frozen scene. It'll be a slow, subtle continuation of processes that began long ago, operating beyond our ability to extract structure from them. Nothing stops, but fewer things happened. That difference is easy to miss, and it is often where the idea of stillness sneaks back in. But once you separate motion from usefulness, the picture becomes clearer. The universe does not end in silence. It fades into uniform motion, and that fading itself is a process, one that unfolds over timescales so long that from where we stand it feels almost abstract. But abstract does not mean static. Even at the quietest edge of possibility, motion remains. One last misconception tends to survive even after all of this is understood. The idea that motion belongs to things, and that when things disappear, motion must disappear with them. But motion does not belong to objects. Objects are temporary expressions of motion. When a structure dissolves, its motion does not vanish. It becomes harder to track because it is no longer confined to a recognizable form. The universe does not lose activity when structures fade. It loses handles ways for us to describe that activity in simple terms. This is why the disappearance of structure often feels like the disappearance of motion. What actually disappears is our ability to summarize what is happening. Early in the universe, there were few structures but enormous amounts of motion. Later, as motion organized itself, structure appeared and the universe became easier to describe. In the far future, structures may become rare again, not because motion has ended, but because it has spread too evenly to support boundaries. In that sense, structure is not the natural state of motion. It is a temporary convenience. Physics reflects this directly. The most fundamental laws do not describe objects. They describe fields, interactions, and changes. Objects emerge only when motion remains constrained long enough to be named. This is why no law of physics requires something to come to rest. Rest is a condition we impose to simplify descriptions. Even when we say an object is at rest, what we really mean is that its motion is either symmetrical, balanced, or irrelevant to the problem we are solving. The motion itself has not stopped. It has been averaged away. This becomes especially clear in modern physics, where particles are no longer treated as tiny solid points. They are excitations, patterns in underlying fields, temporary concentrations of activity. When the excitation fades, the field remains active. Nothing switches off. Seen this way, the universe is not a collection of things moving through emptiness. It is a continuous process, occasionally forming patterns stable enough to be recognized as objects, and then releasing them back into broader motion. This perspective removes the need for a final state of rest entirely. There is no requirement that motion end for the universe to finish. There is only ongoing redistribution. What changes over time is not whether motion exists, but whether it is easy to talk about. And that brings us back to observation again. As long as there are observers, motion will appear as structure, because observers themselves are structured systems that depend on constrained motion. They can only notice change where constraints still matter. Beyond that boundary, motion continues unnoticed. The universe does not need to be still to move on. It only needs to keep changing faster than perfect symmetry can erase. And perfect symmetry, like perfect stillness, turns out to be far harder to achieve than intuition suggests. Which means that motion in some form always finds a way through, not loudly, not dramatically, but persistently, and persistently is enough. There is a subtle consequence of all this that often goes unnoticed. If motion never truly stops, then explanation can never fully stop either. Every explanation relies on freezing part of the universe. We hold some things constant so we can describe how others change. We say assume this is fixed even when we know it isn't. Without that assumption, nothing becomes intelligible. This is not a flaw in science. It is how understanding works. To explain motion, we first pretend that something is still. We choose a reference frame. We define a background. We ignore motions that are too slow, too small, or too distant to matter for the question at hand. Only then can we talk about causes, effects, and mechanisms. What this means is that stillness plays a practical role, even if it does not exist fundamentally. It is a tool, a simplifying fiction that allows motion to be studied at all. This is why physics is filled with idealizations, frictionless surfaces, isolated systems, perfect vacuums. None of these exist in reality, but they allow us to isolate specific kinds of motion and understand how they behave. Once that understanding is in place, the simplifications are relaxed. More motion is allowed back in. Corrections are added. The picture becomes richer but also more complex. Understanding advances by repeatedly freezing and unfreezing motion. This process never reaches a final description. Each level of explanation works only within a certain range of scales. Beyond that range, new motions matter and the old explanation becomes incomplete. This is why no single theory captures the universe in full detail. Classical mechanics works for everyday motion, quantum mechanics for the very small, relativity for the very large. Each theory assumes some forms of motion are negligible, and each breaks down when that assumption fails. Stillness then is not something the universe provides. It is something explanations require, and this requirement shapes how we think about reality. We are trained to look for stable objects, fixed states, and enduring entities because those are easier to reason about. Motion is treated as a deviation from a norm, even though fundamentally it is the norm. This creates a quiet tension. The universe is built from motion. Our explanations are built from stillness. Bridging that gap is what physics spends most of its time doing. Every improvement in measurement, every increase in precision reduces the amount of motion we can safely ignore. Phenomena once treated as static begin to drift. Backgrounds begin to fluctuate. Constants acquire limits. The universe does not change because of this. Our descriptions do, and that is why stillness keeps retreating. Not because reality is becoming more active, but because our ability to resolve motion keeps improving. Each time we look more closely, something we thought was fixed turns out to be moving after all. And once that happens, explanation has to adapt. The process never ends because motion never does. Understanding does not converge to a final frozen picture of the universe. It remains dynamic, adjusting as new layers of motion become relevant. In that sense, explanation mirrors reality. It survives not by reaching rest, but by staying flexible enough to move with what it describes. And that flexibility is the only reason we can keep making sense of a universe that never stands still. If motion never truly stops, then prediction is always provisional. Physics is very good at telling us how motion tends to behave. It can describe averages, trends, and long-term tendencies with remarkable precision. But exact outcomes are another matter. The reason is not lack of knowledge, it is sensitivity. Many systems respond strongly to tiny differences in initial conditions. A small change, too small to measure accurately, can grow over time until the outcome diverges completely. This is not chaos in the sense of randomness. It is deterministic motion amplified beyond our ability to track it. This is why weather forecasts have limits. The atmosphere follows physical laws, yet long-term prediction fails because motion at small scales feeds upward. Errors don't disappear, they spread. The same effect appears throughout the universe. Orbits that are stable for millions of years can become unpredictable over longer spans. Gravitational interactions among many bodies amplify minute differences. Motion remains lawful, but outcomes become uncertain. This does not mean the universe is unpredictable in principle. It means predictability depends on scale and time. Short-term motion can be tracked precisely. Long-term motion often cannot. Stillness in this context would make prediction trivial. If nothing moved, nothing would change. But because motion persists, prediction always has a horizon beyond which certainty fades. This horizon is not a failure of physics. It is a consequence of continuous motion interacting across scales. What matters is not whether prediction eventually fails, but how long it remains useful. In many systems, that window is large enough to support stability. Planets follow predictable paths. Stars evolve in expected ways. Galaxies behave statistically even if individual trajectories vary. The universe balances predictability and uncertainty by distributing motion unevenly. Some motions are tightly constrained and repeatable. Others are free to wander and amplify differences. Both are necessary. Without constrained motion, nothing would last long enough to be described. Without unconstrained motion, nothing new would ever appear. This balance explains why the universe feels orderly without being rigid. It allows patterns to persist while remaining open to change. Prediction works where it needs to and fails where it must. And that failure is not noise, it is information. Uncertainty tells us where motion is free, where constraints are weak, and where new behavior can emerge. It marks the boundaries of stability. From this perspective, unpredictability is not the opposite of order. It is a sign that motion is still active beneath the patterns we observe. Nothing stands still long enough to be known completely. Nothing moves so freely that it becomes meaningless. Between these extremes, the universe unfolds in a way that is structured, dynamic, and never fully finished. And that unfinished quality is not a defect. It is what keeps motion relevant and explanation alive in a universe that never settles into perfect rest. There is an important kind of motion we haven't talked about yet. Not motion that builds structure, not motion that leads to collapse, but motion that goes nowhere in particular. Most motion in the universe does not have a destination. We often imagine movement as a journey from one place to another, a planet orbiting a star, a particle traveling through space. But at many scales, motion is not directional. It is exploratory. Particles wander. Energy diffuses. Systems drift without aiming for a specific outcome. This kind of motion is easy to dismiss because it does not produce obvious change in any single direction. But it is one of the most important reasons nothing ever truly stands still. Consider diffusion. A drop of dye in water spreads out not because the dye wants to go anywhere, but because random motion explores available space. Over time, the dye becomes evenly distributed. No single particle travels far with purpose, yet the overall pattern changes completely. This is motion without intent, motion without a path, motion that still transforms the system. The universe is full of this behavior. Gas clouds spread, radiation disperses, particles undergo random walks through space and time. Even when no forces are acting in a preferred direction, motion continues simply because there are many more ways to move than to remain confined. This matters because diffusion never stops on its own. As long as particles exist, as long as energy is present, random motion keeps redistributing what is available. There is no natural moment when it decides to halt. Stillness would require randomness itself to disappear, and randomness is not noise added on top of motion. It is an expression of motion at scales we cannot fully control or predict. When countless small interactions overlap, their combined effect looks random, even though each interaction follows simple rules. This is why diffusion feels inevitable, not because the universe prefers uniformity, but because random motion explores possibilities relentlessly. Any unevenness becomes temporary unless something actively maintains it. This also explains why structure requires work. Order does not persist by itself. It must be supported by constraints, feedback, or continuous energy flow. Without those, diffusion quietly erodes differences. Nothing dramatic happens when diffusion dominates. Nothing collapses. Nothing explodes. Things simply become less distinct. And that process can feel like the universe is slowing down when in fact motion is continuing just as actively as before, only without producing sharp contrasts. From the inside, this can look like nothing is happening. From the outside, everything is changing. This is another reason stillness is deceptive. Motion does not need to organize itself into visible patterns to be real. It only needs to keep exploring space, state by state, interaction by interaction. Diffusive motion does not announce itself. It does not accelerate. It does not conclude. It just continues. And because it continues everywhere at all times, it guarantees that the universe never settles into a perfectly frozen arrangement. Even when large-scale structures fade, even when gradients flatten, random motion remains gently rearranging what is left. This kind of motion is slow, quiet, persistent. It does not feel like change, but given enough time it reshapes everything, which is why the absence of obvious movement is never evidence of rest. It is only evidence that motion has become evenly spread, and even then it has not stopped. It is simply harder to see where it is going because it isn't going anywhere in particular. There is a quiet consequence of motion without direction that often goes unnoticed. When motion spreads evenly, it begins to erase landmarks. In a system with strong structure, it is easy to tell where you are. There are gradients, centers, edges, differences that give orientation, but as diffusive motion smooths those differences out, orientation becomes harder. Nothing has stopped moving, but nothing stands out anymore. This is why uniform systems feel empty even when they are active. When every region behaves like every other region, motion loses contrast. Change continues, but it no longer produces new reference points. From the inside, this can feel like time itself has slowed down, not because motion has decreased, but because fewer changes register as meaningful. Without landmarks, sequences blur, events lose their order. Motion becomes something that happens everywhere and nowhere in particular. Physics handles this carefully. It distinguishes between motion that creates structure and motion that dissolves it. Both are real, both are governed by the same underlying rules. The difference is whether motion reinforces differences or washes them away. This distinction becomes crucial when we think about why the universe still contains structure at all. If diffusive motion is always active, why hasn't everything already flattened out? The answer is not that diffusion is weak. It is that diffusion is constantly being opposed. Every structure you see exists because something is actively maintaining a difference. Gravity pulls matter together. Nuclear reactions create heat gradients. Chemical processes channel energy along narrow paths. Life itself is a machine for resisting diffusion temporarily. These processes do not stop motion. They redirect it. Energy flows through them instead of spreading freely. Motion is guided instead of wandering. As long as that guidance continues, structure persists. But guidance always has a cost. Energy must be supplied. Gradients must be replenished. Boundaries must be enforced. When that effort stops, diffusion resumes its quiet work and distinctions slowly fade. This does not happen all at once. It does not announce itself. Structures soften, differences blur. What was once sharp becomes gradual. Motion remains, but it no longer serves the same role. This helps explain why the universe looks the way it does at different scales. At small scales, energy flows are intense and localized. Motion is highly constrained and structure is rich. At larger scales, guidance weakens. Diffusion dominates. Motion becomes smoother, more uniform, less dramatic. Neither regime is more real than the other. They are simply different expressions of the same underlying activity, and crucially they coexist. Even in regions dominated by diffusion, pockets of structure can still form where constraints arise. Even in highly structured systems, diffusion is always waiting in the background, ready to reclaim differences when maintenance falters. Nothing ever truly stands still because nothing is ever completely free from either influence. Motion always persists. What changes is whether it builds landmarks or erases them. Understanding this balance matters because it shapes not only the universe's past but its future, and it determines why the universe can feel simultaneously dynamic and uneventful depending on where and how you look. There is another layer to this balance that becomes clear only when we stop thinking about motion as something happening in space and start thinking about it as something happening through states. A system does not have to move anywhere to change. It only has to rearrange itself. Many of the most important motions in the universe are not trajectories. They are transitions, shifts between configurations that occupy the same place but represent different internal arrangements. An atom changing its energy level does not travel. A molecule reorienting does not go anywhere. A material undergoing a phase change remains where it is. And yet these changes matter. They alter how the system interacts with its surroundings. They open or close pathways for energy. They determine what kinds of motion are possible next. This is why motion cannot be reduced to position alone. Much of what the universe is doing happens in spaces we do not visualize easily. Spaces of probability, of configuration of allowed states. In these spaces, stillness is even harder to define. A system can sit perfectly still in physical space while constantly moving through its possible configurations. Thermal fluctuations rearrange bonds. Quantum states shift. Internal degrees of freedom evolve even when nothing external appears to change. From the outside, the system looks quiet. From the inside, it is never at rest. This distinction becomes important when we talk about long-term behavior. Over time, systems tend to explore more of their available state space, not because they are driven to do so, but because motion naturally wanders wherever it is allowed. Barriers slow this exploration. Constraints guide it. But unless the barriers are absolute, motion eventually finds a way through. This is another sense in which nothing ever truly stands still. Even if a system returns to the same outward appearance again and again, it may not return to the same internal state. Change accumulates quietly beneath repetition. This is why aging does not require dramatic events, why materials fatigue, why memory fades. The system keeps moving, but it does so through configurations rather than locations. Stillness becomes a loop, not a stop, a repeated pattern that slowly drifts as internal motion reshapes it. Physics often hides this complexity by focusing on averages, temperature, pressure, density. These quantities smooth over countless internal motions, allowing us to speak as if the system were static. But averages do not freeze motion, they only summarize it. Underneath every steady value lies a distribution. Underneath every equilibrium lies ongoing rearrangement. The universe never commits to a single state for long enough to truly stop. This is not instability. It is exploration. Motion explores space. Motion explores time. Motion explores possibility. And it does so relentlessly whether or not those explorations produce visible change. This helps explain why apparent permanence is so deceptive. A structure can persist for ages while its internal states continue to evolve. When change finally becomes visible, it often seems sudden, even though it has been accumulating all along. Nothing starts in that moment. Nothing ends. The system has simply reached a configuration where its internal motion can no longer hide behind familiar patterns. And because this kind of motion does not announce itself, it is easy to mistake silence for stillness. But silence is not absence. It is motion operating in a register we are not listening to. It's natural to assume that if motion keeps spreading, then eventually everything that can happen will have already happened. That motion should run out of novelty, settling into repetition or uniformity. But that assumption hides a subtle mistake. Motion does not explore possibilities one by one like items on a checklist. It explores them combinatorially. Each new configuration becomes the starting point for many others. Small differences multiply. Interactions overlap. Even when the rules are simple, the number of possible outcomes grows faster than motion can exhaust them. This is why motion does not use itself up. Take a simple example. A handful of particles bouncing in a box. The rules are fixed. The forces are known, and yet the exact arrangement of positions and velocities almost never repeats. Not because the system is unpredictable in principle, but because the space of possibilities is vast. Motion keeps finding new ways to arrange the same ingredients. At larger scales, this effect becomes even more pronounced. Systems interact with other systems. Environments change. Constraints shift. What was once impossible becomes allowed. What was once stable becomes fragile. Motion is not confined to a fixed landscape of possibilities. The landscape itself evolves. This is another reason absolute stillness is so elusive. To be truly still, a system would need not only to stop changing but to stop having alternatives. No neighbouring states, no accessible rearrangements, no nearby configurations it could drift into. In practice, that never happens. Even the simplest systems retain degrees of freedom. Even the most constrained structures exist within larger contexts that change around them. Motion always has somewhere else to go. This also explains why the universe does not repeat itself exactly. Cycles exist, but perfect cycles are rare. Each repetition occurs in a slightly altered context. External influences shift. Internal states drift. Over time, repetition becomes variation. What looks like sameness is actually similarity. This matters because it breaks the idea that motion must lead to stagnation. Uniformity does not imply exhaustion. A system can become uniform in one sense while remaining rich in others. Even when gradients flatten, fluctuations remain. Even when structures fade, internal rearrangements continue. Motion does not depend on novelty in the human sense. It depends on possibility. And as long as systems have more than one accessible state, motion persists. It may slow, it may spread, it may lose its ability to create sharp contrasts. But it does not stop exploring. This is why the universe does not settle into a final configuration that simply repeats forever. There is no final frame, no last arrangement that closes off all alternatives. Motion keeps reopening paths not because it intends to, but because the conditions for total closure are extraordinarily strict. Closure would require perfect symmetry, perfect isolation, perfect cancellation. Each of those is unstable. The smallest deviation reintroduces motion. The tiniest asymmetry opens new directions, so the universe remains open-ended. Not chaotic in the sense of randomness without structure, but open in the sense that motion never fully runs out of room. Even when change becomes subtle, even when patterns last for immense spans of time, alternatives remain nearby. This is not optimism built into physics. It is a consequence of how motion combines, and because motion combines rather than depletes, the universe does not drift toward a single frozen outcome. It drifts through an ever-expanding web of possibilities, some explored, many untouched, all connected by continuous change. Nothing stands still long enough to close that web. There is a quiet implication hidden in this open-endedness. If motion never exhausts its possibilities, then the universe is not simply aging. It is continually re-expressing itself. We often talk about time as something that wears systems down. Batteries drain, stars burn fuel, structures decay, and all of that is true, but it is only one side of the picture. What actually happens is that certain forms of motion become unavailable while others become accessible. A star can no longer shine once its nuclear reactions end, but its matter does not become inert. It enters new states. It cools. It crystallizes. It collapses. It radiates in different ways. Motion does not vanish. Its channels change. This is a general rule. When a system loses one pathway for motion, it gains others. The loss of one kind of activity is the opening of another. What disappears is not motion itself, but a particular way of organizing it. This is why the universe does not move toward silence in the way intuition suggests. It moves toward different regimes of motion. Some are dramatic and energetic, others are subtle and slow, but each regime still involves change. Even in scenarios where large-scale structure becomes rare, internal motion remains. Particles still interact, fields still fluctuate, space-time itself continues to respond to energy and curvature. There is no mechanism that switches these processes off. This also helps explain why the universe resists finality. A final state would require motion to collapse into a configuration with no alternative expressions, no unused degrees of freedom, no leftover fluctuations. But every known physical system retains some flexibility, some room to rearrange. Flexibility is not added on, it is built in. The laws that govern motion do not funnel systems toward a single endpoint. They allow many endpoints, many trajectories, many ways of unfolding. Over time, some paths close, others open. Motion migrates. From this perspective, the universe is not approaching an ending. It is changing the character of its activity. This reframing matters because it shifts how we interpret long-term trends. Cooling does not mean stopping. Expansion does not mean emptying. Uniformity does not mean inactivity. Each describes a redistribution, not disappearance. Stillness would require not just the absence of visible change, but the absence of alternatives. And alternatives persist as long as systems are not perfectly isolated, perfectly symmetrical, and perfectly constrained. Those conditions are extraordinarily fragile. The slightest interaction reintroduces motion. The smallest asymmetry opens a new pathway. And because the universe contains so many interacting parts, such asymmetries are unavoidable. Motion survives not by being strong, but by being inescapable. It is present in every process, even those that look like decline. It is present in every transformation, even those that look like endings. And because it never fully commits to a single form, it keeps reappearing in new guises. What changes over time is not whether the universe moves, but how obvious that movement is. Some eras are loud, some are quiet, none are static, and this continuity, the ability of motion to reinvent its expression without ever stopping, is what allows the universe to remain dynamic, even as familiar structures come and go. One of the strongest reasons absolute stillness never appears in physics is not philosophical at all. It is mathematical. Many of the equations that describe nature stop working the moment motion is forced to zero. Take temperature. At a basic level, temperature measures the average kinetic motion of particles. Lower the temperature and motion slows. But push this idea to its limit and the math breaks down. As temperature approaches absolute zero, removing the last traces of motion becomes increasingly difficult. Not technologically difficult, fundamentally difficult. The closer a system gets to perfect stillness, the more effort is required to slow it further. This is not a practical limitation. It is built into the structure of physical laws. Quantum mechanics makes this even clearer. Particles cannot be assigned both an exact position and an exact momentum at the same time. Reducing motion to zero would require both to be precisely defined. The equations forbid it. Motion is not an add-on to matter. It is part of how matter exists. Even in what we call a vacuum, motion remains. Empty space is not empty. Fields fluctuate. Energy briefly appears and disappears. These fluctuations are not rare exceptions. They are constant. A vacuum is not stillness. It is motion without particles. This matters because it removes the last hiding place for rest. If even space itself cannot remain perfectly quiet, then stillness is not something the universe is capable of producing even in principle. And yet this motion does not look chaotic. Vacuum fluctuations do not tear the universe apart. They average out. They cancel. Their effects are subtle. Motion exists without disrupting structure, which is why we often ignore it. But ignoring motion does not make it vanish. The same principle applies at larger scales. Fields vibrate. Space-time ripples. Gravitational waves pass through regions that otherwise seem calm. Nothing in the universe is truly isolated from motion, because isolation itself would require boundaries that do not fluctuate. This is another place where intuition fails. We imagine stillness as the absence of activity. Physics describes stillness as a limit that cannot be reached. The universe does not approach rest and then stop. It approaches limits asymptotically, never arriving. This is why processes slow down without freezing. Why cooling never eliminates motion entirely. Why quiet systems remain active at scales we do not immediately perceive. The laws do not allow a final halt. They allow only ever smaller motions. And because those motions never reach zero, they always leave room for something else to happen. There is a related idea that often gets misunderstood because it sounds deceptively simple. Inertia. In everyday language, inertia is described as resistance to change. Objects keep doing what they are already doing unless something interferes. This is usually framed as a reason motion persists. But the deeper implication is more interesting. Inertia does not distinguish between motion and rest. It treats them as equivalent. An object moving at a constant velocity is just as stable as an object we call stationary. Physics does not prefer one over the other. The equations look the same either way. What matters is not whether something is moving, but whether its motion is changing. This symmetry quietly undermines the idea of absolute stillness. If motion and rest are physically equivalent, then rest cannot be a special destination the universe is trying to reach. It is just one description among many dependent entirely on the frame we choose. This is why there is no universal definition of standing still. You can always choose a frame in which something appears at rest. You can always choose another frame in which it moves. Neither description is more correct than the other. Motion does not belong to the object. It belongs to the relationship between object and observer. This becomes unavoidable in relativity. Different observers moving relative to one another do not agree on what is simultaneous. They do not agree on distances. They do not even agree on the passage of time. Stillness in one frame becomes motion in another without contradiction. Trying to define absolute rest in such a universe is like trying to define absolute silence in a room where the listener keeps changing position. There is no fixed background to anchor it to. What this means is subtle but important. The universe does not contain a hidden reference frame where motion could finally stop. There is no cosmic stage that everything else moves across. Space-time itself participates in the dynamics. Even the expansion of the universe is not motion through space, but motion of space. Galaxies are not racing away from a central point. Distances between them are changing because the underlying geometry evolves. In such a picture, asking whether something is truly still becomes the wrong question. The better question is whether motion produces measurable effects in a given context. Sometimes it does, sometimes it doesn't. But the absence of an effect is not the absence of motion. It is simply motion that has been absorbed into the frame we're using to describe the world. This is why stillness feels real but refuses to be universal. It works locally, temporarily, and descriptively. It fails globally, fundamentally, and absolutely, and because physics gives no privileged frame where motion can be set to zero, once and for all the idea of the universe ever arriving at total rest quietly dissolves. Nothing has to prevent it. The structure of the laws already does. To understand why nothing ever truly stands still, it helps to ask a more demanding question. What would it take for motion to actually stop, not slow down, not become hard to notice, but genuinely reach zero? To halt motion completely, every form of energy in a system would need to be removed or perfectly balanced. Translational motion, vibrational motion, rotational motion, internal excitations, field, fluctuations, all of it would have to cancel out simultaneously, and not just locally. The system would need to be isolated from everything else in the universe. No incoming radiation, no gravitational influence, no quantum interaction, no exchange of information of any kind. Even that would not be enough, because motion does not exist in one place at one scale. It is layered. Removing motion at one level leaves motion at another. Cooling a material removes large-scale vibration but leaves quantum motion. Eliminating particle motion leaves field fluctuations. Flattening fields leaves space-time curvature. Stopping motion everywhere would require not just perfect control but perfect symmetry across all degrees of freedom. And perfect symmetry is unstable. Any tiny imbalance smaller than anything that can be measured would immediately reintroduce motion. There is no buffer zone. Zero is not a basin the universe falls into. It is a razor's edge. This is why physical systems approach stillness the way they approach mathematical limits. They get closer, slower, and more resistant to further change without ever arriving. The closer a system comes to rest, the more sensitive it becomes to disturbance. The quieter it gets, the more easily noise dominates. Stillness, paradoxically, is the most fragile condition imaginable. This is the opposite of how we usually think. We imagine rest as the default and motion as something that needs to be maintained. Physics reveals the reverse. Motion is the default. Rest requires constant coordination, perfect cancellation, and unbroken isolation. And because the universe offers none of those conditions, absolutely motion survives. This does not mean the universe is restless or turbulent by necessity. It means that calm must be maintained, not assumed. Stability is something that happens within motion, not instead of it. Every stable structure you see, every quiet system, every steady orbit, every constant rhythm is the result of motions that cancel just enough to remain contained while never truly disappearing. Nothing ever fully shuts down. It only becomes finely balanced, and balance by definition is active. This reframes the idea of rest entirely. What we call stillness is not the absence of motion, but the presence of coordination. Motion arranged so precisely that it stops producing visible change. The universe is full of such arrangements. It is not full of stops, and because coordination can fail, shift, or be disrupted, motion always has a way back into view. This is not a philosophical statement. It is a mechanical one. The laws do not permit total cancellation to persist indefinitely. They allow approximation, not completion, which means that even in the quietest imaginable scenario, motion does not vanish. It waits balanced, sensitive, and ready to reappear the moment symmetry slips. Balance often feels like an ending, a place where opposing forces finally neutralize one another and nothing more happens. But balance in physics is rarely static. It is usually dynamic. Consider a system in equilibrium. Forces cancel, flows match. On average, nothing changes. Yet underneath that average motion is constant. Particles collide, energy exchanges, fluctuations rise and fall. The balance holds not because motion stops, but because motion circulates. This is what physicists mean by dynamic equilibrium. A lake looks calm, but water molecules are constantly moving. A stable climate cycles energy between atmosphere, oceans, and land. A living body maintains balance by never resting, continuously correcting itself. In all of these cases, balance is maintained by activity. Remove the activity and balance collapses. This is another reason the universe resists stillness. The conditions that look most stable are often the ones with the most internal motion. Stability emerges not from freezing change, but from distributing it evenly across many pathways. This distribution has an important consequence. When motion is spread across many degrees of freedom, no single disturbance dominates. Small changes are absorbed. Fluctuations are damped. The system appears calm even though it is constantly rearranging itself internally. Stillness from the outside is motion that has been democratized. But democratized motion never disappears. It simply becomes harder to localize. There is no single place where you can point and say that is where the movement is. It is everywhere in small amounts all the time. This is why equilibrium does not feel dramatic. It does not announce itself. It doesn't progress toward a climax. It persists quietly as long as energy continues to circulate. And circulation is key. As soon as circulation stops, balance becomes impossible. Differences grow. Gradients sharpen. Motion reconcentrates. What looked stable begins to drift. This applies just as strongly to cosmic systems. Galaxies remain stable because energy and momentum circulate through vast numbers of stars. Planetary systems persist because gravitational interactions redistribute motion continuously. Even space-time maintains large-scale structure through ongoing dynamical processes. Nothing is holding these systems still. They are holding themselves together through motion. This flips a common intuition. We tend to think motion threatens stability. In many cases, it is the opposite. Motion creates stability by preventing any one part of a system from drifting too far from the rest. Stillness would be dangerous. Motion keeps systems alive. And because the universe is built from interacting systems layered on top of one another, this kind of dynamic balance appears everywhere. From the smallest scales to the largest, stability emerges not by stopping motion but by spreading it out, which means that the calmest looking moments in the universe are often the most active beneath the surface. Nothing ever truly stands still, not because the universe refuses to rest, but because rest as we imagine it is incompatible with balance that lasts. The universe does not choose motion over stillness. It replaces stillness with coordination, and coordination by its nature never stops moving. When systems approach balance, motion doesn't disappear, it changes where it lives. Instead of showing up as large visible movement, it retreats into smaller scales, into fluctuations, into background activity that rarely rises above the threshold of notice. This is why very quiet systems are often the hardest to understand. At low temperatures, particles move less overall, but their relative importance increases. Tiny interactions matter more. Small exchanges dominate behavior. What used to be averaged out now becomes decisive. This is why cooling a system often reveals new physics rather than simplifying it. Superconductivity appears only when thermal motion drops low enough for subtle quantum effects to dominate. Superfluidity emerges when particles coordinate their motions so precisely that friction vanishes. These are not states of rest. They are states where motion becomes collective instead of individual. The same pattern appears again and again. As large-scale motion fades, fine-scale motion takes over. As noise decreases, correlation increases. As randomness weakens, coherence strengthens. Stillness is never what replaces motion. Organization is. This is another reason absolute rest remains unreachable. Removing one kind of motion exposes another. Slowing systems down does not empty them. It reveals layers that were previously drowned out. Even the most carefully isolated experiments encounter this problem. Shield a system from heat, vibration and radiation, and quantum fluctuations still remain. Shield it from those and space-time itself contributes uncertainty. There is always another layer underneath. This layered persistence of motion explains why the universe never simplifies all the way down. Each time motion becomes less obvious, it becomes more structured instead. Less energetic but more coordinated. Less visible but more fundamental. Quiet does not mean inactive. It means concentrated. and concentrated motion is often more consequential than loud motion. It determines ground states, it shapes long-term behavior, it defines what systems can become when disturbed. This is why physics rarely treats calm systems as trivial. They are often the most sensitive, the most constrained, and the most revealing. Small changes in such systems can have outsized effects. Motion when confined to narrow channels gains leverage. This reframes silence one more time. Silence is not the absence of activity. It is the presence of activity that has nowhere else to go. The universe is full of such silences, regions where motion has been compressed into subtle forms waiting for conditions to shift, waiting for constraints to loosen, waiting to expand outward again. Nothing in these regions is frozen, it is poised. And because conditions are never perfectly fixed, poise eventually gives way to change. Motion re-emerges at larger scales, carrying with it the imprint of everything that happened while it was hidden. The universe does not alternate between motion and rest. It alternates between visible motion and concealed motion. And concealed motion is still motion. Hidden motion does not vanish without consequence. Even when it stays confined to small scales, it leaves marks. Every system carries a history of how it has moved. Materials remember stress, atoms remember collisions, fields remember past configurations through correlations that persist long after the original motion has faded from view. This is why systems are rarely as simple as they appear in the moment. Their present behavior depends not only on current conditions, but on how motion has flowed through them before. Physicists call this hysteresis. A system responds differently depending on its past, even if it returns to the same outward state. The same temperature, the same pressure, the same position. Internally, it is not the same arrangement. Motion has rearranged pathways. Constraints have shifted. Possibilities have changed. This is another way motion avoids erasure. Even when it is no longer active in a visible sense, its effect persists. The universe does not reset itself between moments. It carries momentum not just in speed but in structure. This matters because it breaks the idea that systems ever truly start from rest. Every initial condition is already the result of prior motion. There is no blank slate where movement begins. There are only transitions from one ongoing process to another. This is true at all scales. A cooling star remembers its rotation. A solid remembers how it was formed. A region of space remembers past expansions through its geometry. Even space-time itself carries memory. Gravitational waves pass through and leave tiny distortions behind. Curvature evolves in response to energy that is no longer present. Motion reshapes the arena in which future motion will occur. This feedback between motion and structure is crucial. It means motion does not simply pass through the universe. It modifies the conditions under which future motion unfolds. Paths are altered. Constraints are rewritten. What is easy to change in one era becomes difficult in another. Stillness in this context would require not only stopping motion but erasing its history, removing every trace, every asymmetry, every lingering correlation. That would be a stronger requirement than stopping motion itself. And physics offers no mechanism for that kind of erasure. The universe forgets slowly, sometimes never completely. Even when differences fade, correlations can remain buried in noise, ready to reappear when conditions shift. This is why motion feels irreversible, not because it cannot be reversed in principle, but because reversing it would require reconstructing an exact history across countless degrees of freedom. The past is not gone. It is distributed, and distribution is hard to undo. This reinforces a pattern we have seen repeatedly. Motion survives by spreading, by hiding, by reshaping the stage on which it acts. Even when it becomes subtle, it leaves behind altered possibilities. Nothing ever truly returns to a state of zero motion, not even conceptually. There is always residue, always memory, always a trace of movement embedded in what comes next. And those traces matter because they ensure that the future is never a simple repetition of the past. Motion continues not only forward but through history, carrying its influence even when it is no longer visible. So far, motion has been treated as something that happens in time. But at deeper level, motion is part of what gives time its meaning in the first place. If nothing changed, time would be indistinguishable from a frozen coordinate. You could label moments, but nothing would separate one from the next. Without motion, duration collapses into a single featureless point. What makes time feel like time is not the ticking of clocks. It is the accumulation of change. Every clock, no matter how precise, works by tracking motion. A pendulum swings, a crystal vibrates, an atom transitions between states. When we say time passes, what we really mean is that some processes move forward relative to another. This is why time is inseparable from motion. In physics, time does not exist as an independent background against which motion unfolds. It is woven into the relationships between changing systems. Different observers moving differently do not agree on how much time has passed. They do not agree on simultaneity. They do not even agree on the order of distant events. This is not a measurement problem. It is how time behaves. Motion stretches time. Motion compresses time. Motion reshapes what now means. Without motion, there would be no way to define these differences. Stillness would not just halt change. It would erase the structure of time itself. This is why physics does not describe time as something that flows independently. It describes time as something measured by processes, and processes require motion. Even in the most extreme cases, this relationship holds. Near massive objects, time slows because motion through space-time changes. At high speeds, time dilates because motion through space alters how intervals are experienced. These effects are not secondary. They are fundamental. Time is not what motion happens within. Time is what motion creates distinctions inside. This reframes the original question once more. If the universe were ever to reach perfect stillness, time would lose its meaning. There would be no process left to mark duration, no change to distinguish before from after. Physics does not predict such a state, not because it is undesirable, but because the laws themselves are built around motion. Remove motion and the equations lose their reference points. This is another sense in which stillness is unreachable. It would not just be a physical condition, it would be the breakdown of the framework we use to describe reality at all. The universe does not approach this breakdown. It remains active enough to keep time structured. Moments follow one another because something somewhere is changing. Even if that change is subtle, even if it is spread thin, even if it is hidden, time persists because motion persists. And because motion never fully disappears, time never collapses into a single frozen instant. The universe does not move through time toward rest. It generates time by continuing to move, and that generation does not stop. For most of this journey, motion may have felt like something distant, something cosmic, something abstract, but it isn't. Right now, as you're listening, motion is still happening quietly around you. Air molecules drift, heat redistributes. Your body maintains balance through countless small adjustments you never notice. Nothing dramatic is required. The universe does not move loudly all the time. Most of its motion is gentle, repetitive, and easy to overlook. And that is why stillness feels real. Stillness is what motion looks like when it is well balanced. When forces cancel, when change spreads evenly instead of concentrating. It is not the absence of motion. It is motion that has learned how to hide. This is why the universe can feel calm without ever being frozen. Why systems can last for billions of years without standing still. Why time keeps its shape even when change slows down. Nothing needs to stop for things to feel stable. They only need to move together. So when the universe appears quiet, it is not resting. It is coordinating, and when everything seems still, motion has not disappeared. It has simply become subtle enough to let the moment feel complete. That is the quiet truth behind it all. Nothing in the universe ever truly stands still. But most of the time it doesn't need to move very much at all.